Hey Peak Chemsters, this is Mrs. Vanderwall with another edition of Blank Wall video series, and we are in our third installment of the chapter 16, and we are still talking about entropy. Now, here's a great question. What does Jimmy Walker and Alfred Nobel have in common? You guessed it, it's dynamite. So Alfred Nobel was actually the inventor of dynamite and got his fortune with that invention. He also discovered or invented blasting caps and things like that, and he got his fortune. He died basically by himself, all alone, and that's when he gave all of his fortune to a trust to establish the Nobel Prizes. So anyway, what does this have to do with entropy? Well, I'm going to tell you. So if I look at the real dynamite, not Jimmy Walker's version, and I look at the chemical reaction involved, I have 4 moles of C3H5N3O9, and when it reacts, I get 6 moles of nitrogen, 12 moles of carbon monoxide, 10 moles of water, and 7 moles of oxygen. So what does this have to do with entropy? Well, let's find out. Go grab your notes. All right, so we are talking about section 16.5, entropy changes in chemical reactions. In this section, let's start about with chemical reactions that are at constant temperature and pressure. And more importantly, let's talk about reactions involving gaseous molecules. As you might remember, back earlier, we talked about how gases have the highest entropy because they have the most random motion. They can fill up the container because they are zooming around and can have a highest probability of being so random, I guess. And so what if we have an entire reaction made up of gas molecules? What do we do then? Well, it says here the change in positional entropy is dominated by the relative number of molecules of gaseous reactants and products. So if I were to take this combustion of ethane gas and I end up 2 molecules of ethane gas and 7 molecules of oxygen gas, together they add up with 9 molecules. And when they react, note what they got. 4 molecules of carbon dioxide and 6 molecules of water. And together that adds up to 10 molecules. So you go from 9 molecules to 10 molecules, and therefore your delta S increases. And think about what that's saying, that you are increasing the system by increasing its randomness. So let's go back to the dynamite question. So how might this explain the huge amounts of energy that dynamite is able to produce when exploded? You go from 4 molecules of a non-gas, I'm not quite sure what nitroglycerin is, I think it's a liquid, and you go to 6 moles of a gas and 12 moles of a gas and 10 moles of a gas and 7. You end up with 18, 28, 35 moles or if you will molecules of a gas. That is a huge difference. And so you are definitely increasing this randomness, the entropy of the dynamite system when you produce that many gas molecules. So yes, you are going from a fairly orderly nitroglycerin here to a hugely disordered amount of gaseous products. So that would maybe explain part of dynamite's explosive nature. So let's go back to our notes again. Okay, so in order to look at problem number 8, it says predict the sign of delta S. So if you're going to be looking at the thermal decomposition of solid calcium carbonate, let's kind of go back and review what we said earlier, that the entropy of a solid is smaller than the entropy of a liquid, which is smaller than aqueous, and which is much smaller than a gas. So when I go ahead and have the thermal decomposition of solid calcium carbonate, so already I am behind the 8 ball here. So hang on for a second. All right, I had to adjust my smartboard here. And so if I have calcium carbonate and it decomposes, do you remember how carbonates decompose? Let's see here. You're going to make carbon dioxide and then the remainder calcium oxide. And it is balanced, but this is a solid, this is a gas, and this is a solid. So that will help answer the question, is delta S going to increase or decrease? Well, you start off with 1 molecule of calcium carbonate solid, and you make 1 molecule of calcium oxide solid, but what else do you make? You make 1 molecule of carbon dioxide gas. So your delta S indeed does go up. So let me write that down. Because you made that gas, that the delta S increases. Now, what about the oxidation of sulfur dioxide in air? So if I take SO2 and I add oxygen to it, I'm gonna make sulfur trioxide. And what's wrong with this? It is not balanced. So we need to go ahead and balance this. I believe I need to put a 2 here and a 2 here, and I think it's balanced. So these are all gases. And so that doesn't help us with the solid and liquid and aqueous and gas. And so they're all gases. I got to look at the number of gases. And here I have 2 plus 3 molecules of gas total. And here I have 2 molecules of a gas. And what happened? Our randomness went down, actually. Our disorder got a little bit more orderly. It's like taking 3 loads of laundry and combine them into 2 loads of laundry. We have less disorder. So delta S actually decreases, it goes down. So the third law of thermodynamics actually kind of goes through here. And it says the entropy of a perfect crystal at 0K is 0. Why is it 0? There is no disorder. Everything is in a perfect position. At 0 Kelvin, there is no motion. So you cannot have any randomness if there is no motion. So that would be also the third law of dynamics. And what does that do? What is the implication of that? That if you are above 0 Kelvin, which everything is, you are going to have some entropy. There is no 0 in the S columns like we saw with some other things. So you will always have a number with the entropy values. And how does that help you? Well, does this reaction, or does this formula ring any bells? We've seen something an awful lot like that using delta H. But we had said things in their standard state, they have no energy, they have no enthalpy. And so you won't find this oxygen on a chart because it's known to be 0 for the enthalpy. But with entropy, it's a little different. You have to go through and you have to actually look everything up. Nothing is 0. And it says generally the more complex the molecule, the higher the standard entropy value. So let's go ahead and do the next problem and see how this works. All right, so if I gave you the chart with the delta S values, can you go ahead and give me the delta S for the whole reaction? And again, this is just like those that we've done before. I'll just set this up real quick for you, and you work on the rest of it yourself, and then I will show you the answer, okay? So let me just set this up. Delta S for the reaction, all right, is equal to the sum of the delta S of the products minus the sum of the delta S of the reactants. So don't forget, you have to include your moles, because look at that, it is per mole. Try not to be lazy, write it all out. So again, let me get you started. So that's equal to the sum of the product. So I have 2 moles of SO2. And if you look at SO2, it has an entropy value of 248 joules per Kelvin mole. And look what happens to your mole terms. The moles are actually going to cancel out. And then I'm going to add that with 2 moles of nickel oxide, nickel 2 oxide actually, and it has a value of 38. 38, I'm running out of room here, over Kelvin moles, and these moles are going to cancel out as well. That's why you have to write them down. And you're going to then subtract it from the sum, so you're going to add the next 2. You're going to have 2 moles of nickel 2 sulfide, so 2 moles, and again, please write down all your units, and that's going to be 53 joules per Kelvin mole, plus 3 moles of oxygen, and that value is 205 joules over Kelvin mole. And like we did before, these guys are going to cancel, and these guys are going to cancel. So go ahead and do your math, and we'll see how you do. Okay, hopefully you were able to do the work, and you should have found that the delta S for the reaction equals negative 149 joules per Kelvin. And notice what happens. The delta S value went down. It became less disorderly. And does that make sense? Well, I have solid, gas, gas, solid. Well, that didn't really help me. Let's look at our gas molecules though. I have 3 gas molecules going to 2 gas molecules. That's the key. That's what makes it a negative delta S, that we are losing one gas molecule, so we have less disorder. Just to note a couple other things. Notice that your SO2 is a gas, and look how high the delta S value for sulfur dioxide. Notice that your nickel oxide and nickel sulfide are fairly small numbers. That's because they're your solids. So your gases have big numbers because they are that freedom of motion, and your solids have low numbers because they are those crystal arrangements. They are above absolute zero, so they're going to be greater than zero, but they're not big numbers, not like your gases are. So hopefully that made sense to you. All right, let's go ahead and do section 16.3, free energy and chemical reactions. We're going to find out that a lot of this stuff is very repetitive. You're going to see that you can do the same thing with delta G as we did in other things. So the delta G naught is a change in free energy that will occur if the reactants in their standard states are converted to products in their standard states. Delta G cannot be measured directly. We don't have any delta G meters or Gibbs free energy meters out there, not like we have a thermometer. And so the only way you can actually calculate delta G is through other means, using the equations, or you'll see what's coming up here. And finally it says the more negative the value of delta G, the further to the right the reaction will proceed in order to achieve equilibrium. So the more negative, the more your products are going to make. So equilibrium is the lowest possible free energy position for a reaction. You're not going to get any energy out of that. So calculating free energy, there are several methods. Here's method number 1. And so delta G equals delta H minus T delta S. Hopefully that looked familiar. Now look what the chart is giving you. It's giving you the delta H's for this, the heats of formation that we learned back in the earlier chapters. It gave you the delta S values. Notice they're all gases, so they're very similar in size, if you will. I can't think right now the word. And so how are you going to find delta H to plug it in that equation? You're going to have to do that same thing where you have the sum of the products minus the sum of the reactants. How are you going to find delta S? The exact same thing. So once you find delta H and delta S, you can solve for delta G. So go ahead and set those up, and we'll check in and see how you're doing. Okay, hopefully you can follow my work. And I took 2 moles of sulfur trioxide, which is my product, minus the sum of my reactants. So I multiplied those through. Notice that moles are going to cancel out, and so I can do that here. Cancel, cancel. Notice that my 2 moles over here cancels out. And what else do you notice? Look at the value for oxygen. Remember, that's what I had said earlier, that we can find where we have 0 values for enthalpy for your things at standard state, but you'll never find a 0 for delta S. So we end up with the delta H is negative 198 kilojoules, and that is indeed exothermic. So let's see what happens with delta S. Set up delta S the same way. All right, so here's my delta S. Again, is the delta S products minus the delta S reactants. I plug in these numbers. Notice I wrote down all my units. Do you notice that your moles, once again, are going to cancel out? So I can cancel these guys out. And then, oops, I forgot to write down the word mole here. And those guys cancel out, and 1 mole over here would cancel out. I guess I got a little bit lazy, didn't I? So anyway, you end up with negative 187. Look at the units. Joules over Kelvin. Keep that in mind when we plug in for your delta G value. What else do you notice? A delta S is a negative number, so it is becoming less disorderly. And does that make sense? Always go back and see if that makes sense. Yes, it does. We're going from 3 moles down to 2 moles of gases. Notice these are all gases. So delta S should, in fact, be a negative number. So go ahead and solve for delta G. Let's see if this is actually spontaneous, because we have exothermic, which would lend itself to becoming spontaneous, but we have an increase in order or less disorder. So I'm not really sure how it's going to pan out until we actually solve for delta G. So go ahead and plug in this equation right here, and let's see what you get. All right, so here's my delta G work, and notice I plugged in the numbers, and notice I had to convert joules into kilojoules. And here's my final answer, negative 142 kilojoules. It is spontaneous, delta G is negative.